So thank you for the opportunity to be part of your AGS conference. I'm Jen McWhorter, and I'm currently working on my PhD at the University of Exeter and the University of Queensland under the supervision of Dr. Paul Halloran and Professor Peter Mumby. The focus of my work is on improving the way we model climate projections globally over coral reef environments. And more specifically, I'm focusing on the Great Barrier Reef as a case study. Oddly enough, I first became inspired to study the ocean when visiting the reef in Australia at age 10, and I learned how threatened the reef was to climate change. As you're aware, sea surface temperatures are warming as an effect of global climate change. Corals live near their thermal tolerance, meaning they're extremely sensitive to warming temperatures. Corals can be thought of as part animal and part plant. They have an algal symbiont that lives in their tissue called zooxanthellae, as you can see in the diagram here. This gives them the colors that you see on a healthy reef. When corals become stressed, they expel this algae into the water column and appear white. Their tissue is then transparent, and what you're seeing is their skeleton. At this point, the corals are not dead, and they can actually regain this algal symbiont, but if the warming persists, the stress can lead to mortality. This is what a dead reef looks like, and eventually the structural integrity will break down. On a global scale, 2014 to 2017 was an unprecedented period of successive record hot-breaking years, which coincided with the most severe, widespread, and longest-lasting coral bleaching event ever recorded. During the 2014 to 2017 warming event, the Great Barrier Reef was greatly impacted. For scale, the Great Barrier Reef is the largest tropical reef system in the world, nearly the size of the entire east coast of the United States. These maps were created using aerial surveys by Professor Terry Hughes and team, and these aerial surveys captured the last 3 mass bleaching events. These events were large-scale and resulted in a great loss of coral. The bleaching extended even into portions of the southern Great Barrier Reef in 2020. As you can imagine, recurring years of severe bleaching with little time in between provides less of a window for recovery. So now you might be wondering, what can we expect into the future in terms of magnitude and frequency of severe bleaching events? It is important to know that climate models provide useful information of past and future large-scale climate variability, but they have coarse resolutions and they're unable to resolve certain physical complexities over coral reefs. Before I begin diving into my research, I just want to mention that these results have yet to be published. In order to improve climate modeling, we've developed a method to bring in atmospheric inputs from the climate models over the reef and into the water column. Our technique takes into account the bathymetry details, the locations of corals, things like clouds, pressure, humidity, winds, tides, various mixing properties, and then it simulates a vertical one-dimensional heat transport through the water column. We then repeat this simulation over various points on the reef at our specified resolution and within certain depth constraints. The temperatures throughout the water column at each point will have different properties. After running this vertical simulation on the Great Barrier Reef for various climate models, we now have these results. This figure is showing the magnitude or the intensity of warming in terms of coral stress on the y-axis. This is a commonly derived metric that indicates how long a warm anomaly persists over the reef. When this number reaches 8, it's typically when we see coral bleaching leading to mortality. The different lines on this plot are referencing different future climate scenarios in terms of long-wave radiation or energy that's being emitted from Earth. These climate scenarios take into account various socioeconomic and physical processes that cause changes to our global temperature. The highest climate scenario is indicated in red at 8.5 watts per meter squared. This is also known as the worst case climate scenario, and this refers to global average temperatures reaching near 5 degrees Celsius by 2100. The scenario assumes an energy-intensive fossil fuel-based economy. The next scenario is the 6.0 watts per meter squared, and this refers to roughly 3 degrees of global average temperature warming by 2100. And this lends a pessimistic development trend described as little investment in education or health, a fast-growing population, and more inequalities. The 2.6 watts per meter squared scenario accounts for a significant shift in sustainable practices. And finally, the lowest scenario is the 1.9 watts per meter squared. And this is the preliminary candidate for staying below the 1.5 degrees C of warming by 2100. It considers a decline to zero emissions, followed by a long period of negative CO2 emissions. These climate scenarios can range in variability, which is why I show a number of outcomes. It is thought that we might be headed somewhere between the orange and the blue lines. As you can see in the figure, the two low scenarios slightly rise from conditions similar to what we've seen today until about 2048, indicated by the gray vertical line. This is when that lowest scenario peaks. Meanwhile, the high scenarios increase rapidly in the intensity of warming. So those two low scenarios remain close to that 8 threshold where we typically experience severe bleaching. Now that I've showed the magnitude of warming projected for the Great Barrier Reef, as I mentioned, it's important to look at the frequency of these events. If there's less time in between warming events, there will be less time for recovery from bleaching. This figure shows the climate scenarios as when they're expected to experience severe bleaching leading to mortality within a decadal window. As you can see, we have a committed warming of 3 to 4 severe bleaching years per decade, even in the best case, lowest scenario of 1.5 degrees C. For context, if you remember earlier, we've just experienced 3 events in the past 5 years on the Great Barrier Reef, which resulted in widespread bleaching and mortality. In contrast from the lowest scenario, the highest scenario is projected to experience severe bleaching events nearly every year by the end of the century, and roughly 7 out of 10 years around mid-century. Coral reefs support fisheries and tourism. They're one of the most biodiverse spots on Earth, and they've been considered the rainforest of the ocean. Coral reefs not only provide food and tourism revenue for coastal communities, they provide protection from storms by creating a physical buffer. Coral reefs also provide an intrinsic value. We simply like knowing that they're there. For the sake of corals, we need to continue on the lowest possible trajectory. As individuals, it may be hard to see how you can make a difference on such global policies, but by making sustainable choices every day, we can all contribute to reducing our impact on the planet. Other things you can do that will really make a big difference are educate and inspire. This is a photo of me when I was 10 years old on the Great Barrier Reef, and the tour operator informing me of the impacts of climate change to corals changed the course of my life. We can also continue to promote equality, such as encouraging young women to pursue science careers. Thank you for your time.